everyone. Thank you so much for joining us today. I think we're going to get started. We will probably have some additional people join us. They're probably still joining the WebEx. So this webinar is being recorded. We are going to be posting it on our YouTube site. So keep an eye out on our social media pages, and via email we will send out all that information to you so that you can have access to the recording of this webinar. If you are experiencing any audio issues, you can send them in through the chat. All of the microphones are going to stay muted throughout the presentation. There will be time. There will be a time after each presentation. We have 2 presenters today. There will be time after each presentation for questions. So we ask that you save your questions until that time. You can send your questions in through the chat panel, and we have a moderator who will be reading those questions for everyone. We ask that you keep your video off unless you are speaking, and so that's just a little bit of the housekeeping. So at this time, I will pass it over to Matt McCarty. So he is the co-chair of PIANC USA for our Young Professionals Commission. So thank you again, everyone, for being here. Go ahead and take it away, Matt.
Great. Thank you, Kayla. Thank you, everyone, for tuning in. I'm really excited about our presentation today. We've 2 awesome speakers and presentations lined up. Mr. Benjamin Popovich on tsunami resilience of pile-supported wharves, and Mr. Adrian Pearson on state of practice for monopile designs. Some additional quick housekeeping. We're shooting to keep today's presentation for about an hour, so we'll have some opening remarks. Then the first presenter, brief Q&A, second presenter, brief Q&A, and some closing remarks. And then both presenters very kindly offered to stay on the line if there's additional questions or open discussion period. We're very much encouraging you to ask questions and try to make this interactive. Next slide. Great. So a bit about your hosts today. PIANC USA Young Professional Commission, YPCom. Our whole leadership team, almost the whole leadership team is on the line today. Myself, Mr. Matthew McCarty, representing the New York City area, Andrea Viteri out of San Diego, Nick Stefani out of Madison, Wisconsin, Nicole Pauly out of Tampa, Florida, and Kayla Waltmeyer out of Washington, D.C. You can see strategically we have kind of the 4 coastlines of the United States covered by design. So in pre-COVID times, we used to do a lot of construction tours and technical tours, presentations, and happy hours. Some of our recent events from last year are photos in the bottom right-hand corner, and we hope to get back there soon. But for the time being, we've transitioned to this digital platform and giving webinar-style presentations. But we welcome feedback. We're adapting to this new medium like everyone else is, so we welcome feedback. Next slide. So, and then taking a step back further, PIANC, not everyone may be familiar. PIANC, it's a nonprofit global organization providing guidance for sustainable waterborne transport infrastructure for ports and waterways. It is very much an international organization. It's headquartered in Belgium. And aside from career development of its members, a core mission of the group is to really identify developments, new technologies in our field, collect pools of industry experts from all over the world, develop working groups, and then develop best practices manuals out of them on how we can best adapt as an industry to these changes. So within PIANC, there's several commissions, technical commissions, and then membership. It's okay, we can skip to the membership, the global picture. As you can see, there's over 40 member nations. Again, it is very much an international organization with representation on almost all the continents. And a lot of these countries, we're very, I'd say, fortunate in the United States. We have institutions like the Army Corps of Engineers and American Society of Civil Engineers that help us kind of fill out our engineering toolbox of standards and manuals. But a lot of these countries, the PIANC best practices manuals, it really takes on almost a code-like status. Is tremendously important in those countries. Next slide. And that segues in today's presentation. So our 2 presenters won this year's Paepe-Willems Award, the first and third place. So this is really the premier young professional award given internationally in PIANC every year. It's for young professionals, 40 years and younger. It's a pretty generous definition of a young professional. And it's given it's a paper competition. Generally, paper is about 20 pages long, and it's meant for, it recognizes papers that really contribute to best practices, the state of practice within the industry, have immediate implications for adoption and advancement within the industry, and less towards kind of the theoretical side. And so it was a banner year for the United States. We actually, Mr. Benjamin Popovich, who we're claiming as an American, who's currently living in New Zealand, won the first place prize, and Mr. Adrian Pearson won the third place prize. And an American hasn't won this award since 2016, and I was actually the one who won it in 2016. Those are my photos below, getting the award in Bruges, Belgium. And it was really an amazing experience. The top prize is 4,000 euros, and you get to present at the annual General Assembly, which is the aggregating of the delegates, the executives from those 40 countries into one room. So it's a very prestigious audience that you're presenting to, and it was really an amazing experience. Next slide. And so we'll get the first presenter going here, Mr. Benjamin Popovich. He's currently living in New Zealand, but is originally from New Jersey. So we're claiming as an American for this. New Zealand, may want to claim him too. But so Ben works for the National Institute of Water and Atmospheric Research in Wellington, New Zealand as a hazard and risk analyst, and he completed a PhD in civil engineering at the University of Auckland in 2018, and he will present on tsunami resilience of piers. And again, I'll repeat, we encourage questions. Please submit them using the chat box, and we'll have a Q&A period following his presentation, and he'll be able to address them. So take it away, Ben.
Great. Thanks a lot, Matt. Let me just share my screen here. So I just want to start by giving a big thank you to PIANC USA YPCom for inviting me to speak here. As Matt said, I'm an American, but I'm currently living overseas in New Zealand, in Wellington, which is actually the capital of New Zealand. And I work for an organization called the National Institute of Water and Atmospheric Research. That's quite a mouthful, so we just shorten it and say NIWA instead. And I'm going to talk today about some work that I've been involved in for some time now between NIWA and the University of Auckland up in the city of Auckland that relates to assessing the structural resilience of New Zealand port structures, and more specifically pile-supported wharves, to tsunami loading. And even though this work is obviously done in the context of New Zealand, it's quite applicable and can be extrapolated to structures overseas that are of a similar typology. So I recognize I live in a bit of an obscure corner of the world, and there's probably a lot of people on the call who really don't have any contextual knowledge of New Zealand, so I'm going to do my best to provide as much background and information as I possibly can to make this a bit more engaging. We're a small little country in the South Pacific, and we lie right on top of a major convergence plate boundary, where the Australian and the Pacific tectonic plates meet. And as a result of that, we're potentially exposed to large earthquakes. There's volcanoes that dot the North Island, and of course, we're also potentially exposed to tsunamis, which are secondary effects of those. And for this work in particular, we were looking at tsunamis, and the reason for that is because earthquakes and volcanoes to some degree are generally accounted for in structural design guidelines, in New Zealand at least. Tsunamis really aren't. It's not really as well understood how structures react to the type of loading that they exert on the structures. So it was worthwhile to take a step back and look at that, since it hasn't really been examined in any great detail. And New Zealand, over the past century and a half or so, has been hit by somewhere between 40 and 50 tsunami. They've varied in magnitude by quite a bit. So these two images are showing the source locations for a number of different tsunamis that have hit our coastlines. Most of them have been on the order of centimeters rather than meters in terms of wave amplitudes on the coast, but some of them have been quite large, particularly those that have been generated off the South American coastline that have been up to 3 to 4 meters on the coast of New Zealand. Some of the local ones, especially along the northeast coastline, that's called the Hickory Trench up there. That's a major subduction zone. And the earthquakes that occur along there have generated tsunamis that have been up to 10 meters on the coastline. Fortunately, they've hit outside of the major cities. New Zealand has been relatively fortunate in a couple of ways. Number one, when those tsunamis have hit. In a lot of cases, it's been low tide, which has really mitigated the impacts. And in other cases, they would have hit decades and decades ago. And over the past several decades, the coastlines have really built up in terms of the infrastructure and the populations that are living along them. New Zealand's major cities pretty much all sit on the coast. So Auckland, which is the biggest city in New Zealand, Wellington, which is the capital, Christchurch, which is the biggest city on the South Island, are all coastal cities. If the same events were to hit the coastline today, we would probably expect to see quite different impacts as opposed to decades ago. And of course, ports inherently lie on the coastline. We don't really have a lot of river ports in New Zealand. Everything is pretty much on the coast. So that type of infrastructure would be one of the first bits that would be inundated by such events and potentially subject to major impacts. And because New Zealand is a very import-export based economy, that would obviously have very, very big implications for the well-being of the country. So with that kind of as an introduction, the work that we undertook was to examine how well that infrastructure would withstand such events, such tsunamis. And because ports, of course, encompass a wide variety of different types of infrastructure, the focus here was specifically relegated to pile-supported wharves, which are the dominant type of wharf in New Zealand. We don't have a lot of quay wall type structures. And this has the intention of kind of being able to go back later and re-examine other types of infrastructure within the ports that might also be of interest. So this work was carried out in a number of different phases, and I guess they can be really categorized in two pipelines. And the first pipeline focuses on the tsunami hazards themselves. So that meant a series of hydrodynamic modeling that was meant to come up with potential wave amplitudes and current velocities and whatnot specifically at the port locations. And then that information translates into loading characteristics, both in terms of magnitudes and in terms of time series that they would be applied to infrastructure over. And then the second pipeline relates to the infrastructure itself. So that means collecting as much data as we can on what sorts of structures currently exist at the ports. And sometimes that information is quite sparse because some of the infrastructure dates back quite a ways. The infrastructure is quite old on some sites. And then from the data that we collect from the ports, we developed structural models, and the tsunami loading characteristics were applied to those structural models, and we're going to come up with predictive damage states for such events. And I'll talk a little bit more about each of those different phases a bit later on. So just on the ports a little bit. Let me get this out of the way. I assume everybody can see that. It's blocking my pictures. So New Zealand is home to 14 major ports that really dominate the bulk of the import and export shipping, as well as the inter and intra-island domestic shipping. There are 7 on the North Island and 7 on the South Island, and they cover almost all of the coastlines, with kind of the only exception is really the west coast of the South Island, and that's because it's very sparsely populated. Of course, on the other hand, that's also the coastline that has all the fjords and all the glaciers, so it's got its own benefits in its own right. And the one port that does lie on the west coast of the South Island, Westport Harbor, that's by far the smallest port in New Zealand, and in fact has really shuttered all imports, all international shipping, and a lot of its major clients have downsized in recent years. So, in fact, that port was ultimately not examined in the hydrodynamic modeling and in the structural modeling, but all of the other 13 ports were. And these are some images of some of the bigger ports in New Zealand: ports of Auckland, Littleton, and Port of Tauranga. And of course, all of the 13 ports that were ultimately examined bear a pretty great degree of importance, especially for the regions that they service. They all service the primary industries that operate within those regions, and they're quite diverse in terms of the markets and the industries that they service. There are certainly some key sites that bear national importance for New Zealand, and those include the ports of Auckland, which actually has 2 sites, one on the north end of Auckland in Waitemata Harbor and one on the south end in Manukau Harbor, and Waitemata is the really, really big one. And Ports of Auckland is the biggest port in New Zealand, and it also services the largest city. So Auckland is about 1.5 million people out of a total population in the country of about 4.5 million people, so about 33% of the entire population lives there. Then Port of Tauranga is the primary export port in New Zealand. That's about 2.5 hours by car to the southeast of Auckland, so relatively close in terms of distance. Northport is a port that lies way on the north end of the North Island. And that port is particularly important because it services the Marsden refinery, which is New Zealand's only oil refinery. and that site is responsible for producing close to 100% of all the jet fuel, the ship fuel oil, the diesel, and the petroleum that's consumed in New Zealand. So basically everything that moves and doesn't have legs is kind of reliant on that site and the port that services it. And Littleton is the key port on the South Island because it services the largest city on the South Island in Christchurch, and there really aren't any other ports on the South Island that even come close in terms of the size, so it would be difficult to redirect shipping if that site was to go down. And as an added note, that site, Littleton, was actually pretty badly damaged following the major earthquakes in 2010 and 2011. There was quite a lot of work that had to be done to get that back up to operation. So one of the first things we looked at in developing damage models is we looked at, okay, we were looking at a specific type of infrastructure. So what's happened in the past when these types of events have hit and done damage to this type of infrastructure? And I reiterate that tsunamis really haven't done too much damage to the infrastructure in New Zealand, along New Zealand's coastline in particular. So in order to get an idea of what sorts of damage we would expect to see, it's necessary to look overseas to other countries. And there have been two really major events over the past couple of decades, and then a number of smaller ones as well that have done some damage. But the biggest events in the last couple of decades have really been the 2004 tsunami in the Indian Ocean and the 2011 tsunami that occurred off the coast of Japan. And both of those did major damage to the infrastructure in the countries that were nearby them. And so these two images come from a field survey that was done in Thailand following the 2004 Indian Ocean tsunami, and they're kind of indicative of damage that we've seen, obviously in this survey, but in others as well, to pile-supported wharves. The tsunamis come in and they exert extremely high lateral hydrodynamic loading that does damage directly to the piles, and they also do a lot of damage in terms of the uplift that they exert in the underside of decks for open-style structures. So the waters come underneath and rise very quickly and exert very, very high magnitude loads on the undersides that can do a lot of damage to the connections and also to the deck members themselves if they're not sufficiently reinforced. And I guess I should point out, Thailand is obviously a very different country than New Zealand or Japan or the United States are. The design standards in different countries are going to be very, very different, the structural design standards, and so we would expect that the structures would respond quite differently depending on the country, but it's still useful to look overseas when that's the only data available, really, to gain some kind of indicative idea of what sorts of or what modes of damage we would expect to see in these sorts of events. And New Zealand, there are issues that New Zealand faces, and there are issues that aren't necessarily unique to New Zealand, but it certainly does face. And one of those is that many of the ports in New Zealand are built on reclamations. So this picture is the city of Wellington. That's actually where I live. That's the capital. And the port here is called Centreport. And the port is built on reclamations that date back, in some cases, over a century. And it's kind of interesting because it's not just the port that's built on the reclamations. It's actually the entire downtown area of the city. If you look at maps of the city of Wellington that date back to the 1800s, basically everything is underwater. And now everything is built up with skyscrapers and whatnot. And that has led to issues in hazard events in the past. So in 2016, there was a major earthquake, about a 7.8 moment magnitude earthquake on the northern end of the South Island in a town called Kaikoura. And Wellington isn't that far away from that by distance. And the earthquake caused settlements of the soil right behind the wharves, and that land dropped by between 2/3 of a meter and a meter, so about 3 feet it dropped behind the wharves. And although this is earthquakes, tsunamis can also, they can really do a lot of damage to the soil because of the turbulent nature of the tsunamis. So if it's not compacted well, you could see similar damage from tsunamis as well as from earthquakes. So that's certainly an issue that New Zealand may face in the future with the reclaimed land. So what do we know about tsunamis in New Zealand? And this is really focused, I guess, specifically on New Zealand. There have been a number of national tsunami assessments that have been done, but like in other places, national assessments are usually done on a very coarse scale. So for New Zealand, the most recent national tsunami assessment was done back in 2013, at least the major one. And the issue with that is that tsunamis were modeled on 20-kilometer intervals along the coastline, and obviously that's not a lot of use if you're looking at hazards directly inside of the ports, because chances are that the ports may not lie at the point of that maxima if it's only occurring within a window of 20 kilometers along the coastline. So in order to assess tsunamis within the ports, we need much more site-specific results that are focused on specific lengths of coastline. And that led to a series of running hydrodynamic propagation models. So a propagation model is basically a model that predicts wave heights and current speeds at locations along the coast. And they can be based on a number of different inputs. In this case, we were looking at subduction zone earthquakes, but propagation models can take inputs from fault line earthquakes or from landslides or just about anything that can produce a tsunami. And in order to run these hydrodynamic models, you need very good bathymetric data for the coastline that you're looking at, and you need to have some sort of source model. Again, in this case, we're looking at subduction zone earthquakes, but could be other things. And these were run using a program called COMMIT, which is the Community Modeling Interface for Tsunami, and that's actually developed by NOAA in the U.S. So we developed bathymetric maps for each of those 13 ports. This is, again, Centerport in Wellington. All the data for that came from an organization in New Zealand called LINZ, Land Information New Zealand, which is responsible for maintaining topographic and bathymetric data sets. And those bathymetry grids were built on 10-meter grids, at least at the locations of the ports. So it's quite fine in terms of the resolution once you get into the actual site. And in terms of source models, we modeled earthquakes from 3 different local source locations and 3 different distant source locations. So the local sources kind of reflect the major subduction zones around New Zealand, which are the Kermadec Trench, which is just to the north of New Zealand, the Hikurangi Trench, which is probably the biggest threat to New Zealand, and that lies just off the eastern coastline of the North Island, and the Poiseuille subduction zone, which is a bit smaller, down south of the South Island. And then in terms of the distant source tsunamis, we modeled 3 locations as well, from the Solomon Islands, from Peru, and from Chile. So the outputs of those propagation models are maximum water levels for each of the sites. So these are the maximum water levels inside each of those grids for each of those ports. And there's certainly sites that are more exposed to tsunamis than others, and none of this, I mean, from a New Zealand context, none of this really comes as a surprise because there are so many subduction zones surrounding the Pacific Ocean. It's kind of long been known that the east coast of New Zealand is particularly exposed to tsunamis, and the same kind of exposure would probably relate, without having modeled it, would probably relate to the western coastline of the United States, just because there's so many major and active subduction zones surrounding the Pacific that can generate distant source tsunamis that really do a lot of damage to the coastlines where they hit. And same thing for current speeds. The ports that are potentially exposed to very high current speeds are mostly the same as those that are exposed to very large tsunamis as well, though not in all cases. It's worth pointing out that current speeds and wave amplitudes can even exclusively, in the absence of the other one, do quite a bit of damage inside of the ports. So even if you don't have a necessarily tall tsunami, it can still do quite a lot of damage if the currents are moving very quickly. And just an example of what one of those final grids looks like. So this is for Northport, where the fuel refinery is. So those plots on the left are showing the maximum wave amplitudes across the entire grid surrounding Northport and the maximum current speed surrounding that port. And you can see in the images on the right. So the top one is just an overview of where Northport is at the entrance to what we call Whangarei Harbor. That's that inlet there. And then on the bottom, you can see that's taken from the mountain across the entrance to the harbor. And you can see the port off to the right side, and then you can see the refinery that it services on the left side, sitting right on the edge of that peninsula. So the second phase of work surrounded determining magnitudes and modes of tsunami loading. So tsunami loading is a bit complex, and it's usually broken down into a number of different parameters. And they can be categorized as horizontal and vertical loads. The horizontal can include things like wave slam, surge forces, hydrodynamic loads, hydrostatic loads. And the vertical loads can include things like buoyancy, gravity loads, if you're talking about a flat surface, and uplift, and hydrodynamic uplift. And especially recently, there have been some design standards that have started taking into account tsunami loading and providing design equations and whatnot, particularly some design standards that have been published by organizations like FEMA. And more recently, the most recent revision of ASCE 7 also included a section on tsunami loading and tsunami design. And the one component of that loading that's often left out because it only applies to certain types of structures is really the hydrodynamic uplift. And in fact, to quantify that particular type of loading, there was actually a long series of physical modeling that was carried out at the University of Auckland's Fluid Mechanics Laboratory. They have quite long flumes, up to like 30 meters or something like that, where there was a series of testing done on specifically pile-supported Warf-type structures, scale model structures. And so we came up with load magnitudes, and then those load magnitudes were developed into time series that were ultimately applied to structural models that we created based on data we got from the ports. And I'll talk about those structural models in just a second. So the time series consisted of two phases, basically an initial impact phase and then a steady state hydrodynamic phase that were applied to the structural models, to each pile in the structural models. And so the second kind of pipeline of work that we undertook was developing structural wharf models. And these were based on data that we got specifically from the port companies. So one thing to point out is that there are 14 port companies in New Zealand, and they're privately owned, and they're also highly competitive. So the data that they release is subject to commercial sensitivity. So rather than modeling any specific wharf, all the data that was collected was kind of aggregated into generalized models. And those were modeled for three different time periods, pre-1963, 1963 to 1989, and 1989 to present. And the distinction between those time periods is that's when there were major revisions to New Zealand's concrete and reinforcing steel structural design standards. And obviously, there were a lot of different characteristics that went into the development of the Warf models. That would be something that I could probably do an entire talk on, to be quite honest. But we modeled things like different soil types, different grades of steel reinforcement, different shapes and sizes and dimensions of piles, et cetera, et cetera. And so the tsunami loading characteristics were ultimately applied to those Warf models that we generated, and we came up with element damage states for each of those structures, for each of those unique tsunami scenarios. And the element damage states were applied to each element inside of those structural models. And in order to keep things relatively general and not introduce too much over-certainty into this modeling process, we just developed 4 damage states, and they're quite broad, so it's elastic if there's no sustained damage to that element, cracking when the concrete begins to crack on that particular element, and then 2 higher damage states that relate to the reinforcement, yielding and fracture. And after those element damage states were applied to the structures, all of that data was aggregated into damage states that describe the damage to the entire structure itself. So that would be, no damage to begin with, and then concrete, and then the point at which concrete cracks related to the wave height of the tsunami, and then potential yielding and fracture of the reinforcement inside of that to potential fracture of the pile. And that data was aggregated and pulled together for each different structural model that we generated. So this is one soil type, and it relates to all of the different time periods that we modeled, the different sizes and shapes of piles, and that yield strength low and high bit that relates to the New Zealand's steel reinforcement design standards. There are 2 grades of steel that are used right now. I think it's 300 and 500 megapascals. And that's been consistent over time. They've just increased over time. Just a couple of final thoughts before I close up. So this assessment really focused in on wave amplitudes related to damage, and that's in part because a lot of the design equations that are available really focus in on wave amplitudes, although it's increasingly becoming more common to see current speeds and velocities also incorporated into those equations. But obviously the currents also have the potential to affect structural performance, and especially it can depend on the harbor's natural frequency and whether there's wave excitation taking place. There are certain ports that do tend to see effects like that. And second, there's a great difficulty in determining ARIs for tsunamis, especially because they're linked to source events that also have ARIs and AEPs associated with them. So it can be highly speculative as to how often and common certain events will occur and certain damage will occur. And with that, I'd just like to thank PIANC USA YPCom again for inviting me to speak. And I think questions were getting typed into the chat bar, but if you do have anything further that you'd like to comment on or question, then my contact details are here, and please don't hesitate to get in touch. Thank you.
Thanks, Ben. I think we're right about on time. I know I put a question in the chat. That was really interesting stuff. So feel free to type them in now, and then there will be probably a final opportunity at the very end, but I encourage you to put them in now. So right at the beginning, you were talking about the uplift issue on the open wharf decks, and it seemed to be very much kind of the critical issue you were evaluating. And this isn't the subject of your research, but I'd like to hear your opinion on, I guess, the vulnerability of the bulkhead and solid quay walls or quays versus the open deck wharf structures. And is that something, your thoughts on that maybe for a new build in your area of the world?
Yeah, so I would definitely say, again, this was evaluated against the specific types of structures that are located here, and there is certainly a reason that they build those types of structures, and one of them is that tsunamis tend to have a much kind of wider return period or annual exceedance probability than earthquakes, for example. It's very common for earthquakes to hit the shores, and I think the general consensus is that the pile-supported structures tend to respond to the earthquakes, so it's not necessarily the tsunamis that are coming into consideration when the decisions are to build that kind of structure. It's more the earthquakes. But in terms of the pure tsunami vulnerability, I would definitely say that the quay wall type structures are much more likely to perform better against those tsunamis, and in part that is because it doesn't have the potential to flow underneath and produce those high magnitude loads on the decks. It's kind of similar issues that we see in bridges as well in New Zealand, and we get a lot of river flooding and stuff around here too, and we do see similar types of damage coming from those events on those types of structures as well.
Got it. Thank you. And we just had a question come in. Was the structural analysis performed with the peak/impact load from the wave applied as a static, some equivalent static load less than peak, or nonlinear time history for each structural element? We actually did a few different analyses. We did apply it as a static load to see what would happen. Ultimately, that time series that was displayed there was what was applied directly. We did that through a program. It's a kind of obscure structural analysis program called OpenSeas, and it's not something that would really be seen as a consultancy tool because it requires really coding models. But it does give a lot of power over how loading is applied to the structures themselves. So we can code specific time series when we're applying those loads to the structural models that we develop. But we did it a few different ways and looked at it a few different ways. Got it. Thank you.
I just saw another question come through that I think I'm going to just answer.
Yeah, go for it. The structural analysis software.
Yeah, so that's a program called OpenSeas, which is an open source. It stands for Open System for Earthquake Engineering Simulation, I think, and it's probably more of a research tool than it is a consultancy tool, but it's quite powerful in terms of what it can do as far as structural analysis goes. It just requires a bit of kind of coding rather than working through like a user interface type model setup. But other than that, it operates behind the scenes similarly to other structural analysis software.
Got it. Thank you. Maybe just like one or two more. Was there a slide that showed? It seemed to show that the 1963 construction actually performed better than or maybe had a segment that it showed damage but not maybe fracture rather than the more contemporary, or I may have just interpreted that slide wrong. It was like a section view, I think.
In general, the earlier wharves, specifically because the grades of steel that were used were much lower, generally performed worse than the later ones. There's a bit of back and forth because I'm trying to go back. In general, those structures did perform quite a bit worse than the structures of today. It's just I guess one of the things is that as the steel's gotten stronger, it's also gotten a bit more stiff. and that, yeah, if it's applied to hazards that kind of feed on a lack of flexibility, then that can potentially have impacts for the structures as well.
Got it. Okay. And maybe last one. Could you elaborate on the model testing that you used? And then this particular person, you may want to know that we use the pneumatic tsunami generator at Wallingford. So I'm cautious of testing using waves that are far too short.
So we tested in terms. This is in terms of the physical modeling, I guess, correct?
That's the way I'm interpreting it.
I'm guessing. Yeah, I'm guessing that's what the. So we actually did this. We actually did the study. I didn't go into too much detail on the physical modeling side of things. That's also quite a long series of work. But that was actually done in a couple of different ways. So we did that in two different flumes. The first one we generated solitary waves, and the second one we generated what was kind of analogous to a dam break type bore. That was the one that was ultimately used to quantify the uplift loading, because that's a bit more representative of what you would actually expect to see in terms of tsunamis. The solitary waves tended to understate the magnitude of the uplift loads, but it was more bore type rather than a sinusoidal wave type that was actually used to quantify that in a kind of dry bed that a hydraulic gate was just raised very quickly in order to create a bore.
Got it. Thank you. Ben, excellent job. You're sticking around, but let's transition to our second presenter, Adrian.
Great. Thank you so much.
Okay. Adrian, and I think you're sharing your screen, or you will be.
Here we go.
Yep. Excellent. All right. Thank you. So this brings us to Adrian Pearson, presenting on mooring loads and considerations for monopile dolphins. Adrian is a marine structural engineer with Moffitt-Nichol in Long Beach, California. He earned his 5-year integrated Master's of Civil Engineering from the University of Edinburgh, where he focused on structural and geotechnical engineering. He is also a member of the newly formed Working Group 231, Mooring Bollards and Hooks. Take it away, Adrian.
Great. Thanks, Matt. Hello, everyone. My name is Adrian Pearson. I'm a marine structure engineer with Moffitt-Nichol in Long Beach, California. Moffitt-Nichol, we're a global infrastructure advisory firm based in the United States. Got offices in 7 different countries, and we provide services to clients in the marine terminal, transportation, environmental, energy, and urban waterfront development markets. And today I'm going to be speaking about a project that I worked on in Lake Charles, Louisiana, at the Port of Lake Charles, and specifically about a mooring upgrade project involving monopile mooring dolphins. So to situate everyone who may not be familiar with the geography of Louisiana, Louisiana is in the southeast United States, and Lake Charles is in the western part, so quite near the Texas border. And Lake Charles is located on the Calcasieu Ship Channel that comes in from the Gulf of Mexico. It's about 30 miles inland. And Port of Lake Charles has several facilities, 2 bulk terminals, and then also what we're showing here is its largest facility, City Docks, which is a 200-acre facility. It's got 12 deep water berths and about 1.6 million square feet of covered shed space. The project that we're looking at here, berths 4, 5, and 6, run north-south on the Calcasieu River, just a continuous timber wharf with a covered shed on top. So I want to speak a little bit more about this project in specific. Berths 4, 5, and 6, as I said, are timber wharves with sheds on top. And these berths are primarily used for break bulk cargo, so palleted bags of rice or other types of grain. But it's also used as essentially a parking spot for oil tankers that are waiting for the liquid berths to open up nearby. So they see large Panamax class break bulk ships as well as oil tankers. And as you can see here, the primary mooring equipment are just cleats that are primarily designed for barges, but they're being used more and more often for these large tankers with stronger mooring lines. And you can see here in the photo that the cleat has 3 lines tied to it, and you can see the actual timber bull rail to which the cleat is connected is starting to pull away from the wharf deck slightly. And you can see on the right the result of that more and more frequently is these cleats actually getting ripped out of the timber bull rail. So that was the motivation for the project at its birth, is to upgrade the mooring equipment. And to do this, we decided, because a full wharf rebuild was not a full wharf rebuild was not possible in the short term, we decided to install isolated mooring dolphins within the existing footprint of the structure to provide a strong mooring point and not to rely on the existing timber wharf to resist these large mooring loads. And I want to speak a little bit more now about the design of these mooring dolphins, and just to step back for a moment and talk about what really governs the design of these dolphins is the mooring load that's applied to it. These ships often have mooring loads with very high minimum braking loads that can exert very large lateral forces on these dolphins. So typically the mooring load governs the design of these dolphins. And when we go to calculate these loads for use in design, there's several different methods. One is you can run a numerical mooring analysis in software where you can model the berth structure, the ship, the mooring lines, and run all different conditions of wind, wave, current, and you can actually calculate how the system responds and what the tension is in each line. You can also run a model, scaled model in a laboratory where you can simulate the ship at berth and how it responds to different environmental conditions. And then you can also use simplified equations that are just based on the number of lines, the geometry of the berth, to figure out what the total load is on your dolphin. And PIANC, specifically this document that's shown here, report number 153, is used all over the world for the design of petrochemical and gas terminals for vessels. And we use these guidelines on many different projects, and for this project at Porto Lake Charles, we decided to use this as the reference. And before I move on to the specific project, when we approach the design of a mooring dolphin, we want to, whichever method we choose, we want to achieve the same ultimate design where we have a progression of strength from the ship to the dolphin, so that in the case of an overload, if something goes wrong at the terminal and the ship line experiences an excessive tension or something goes wrong, that the last thing to happen is a cleat, bollard, or hook to rip out of the wharf deck, which could injure personnel, could damage the ship. And then also, if a bollard pulls out of a wharf, that means that that berth may have some downtime in order to fix that and bring ships in for the next call. So the goal is to design a system that is progressively stronger from the ship to the dolphin, and I'll speak about that a little bit more in the next slide. I'm going to focus here on the simplified equations versus the mooring analysis and look at how these loads compare in design. So to jump into the details, the PIANC guideline that I showed before defines an equation that tells you if you're designing a dolphin that has mooring equipment, be it bollard or hooks, it gives you an equation to calculate what is the total horizontal load applied to the structure that you need to design for. And you can see here, this is a function of how many lines are tied to this mooring point. So in this photo on the right, you can see this has 2 hooks, 2 mooring lines. It's a function of what the safe working load of the hook is. So if you have a 100-ton hook with 3 lines, you can calculate what the total load is. And then it's got a factor here on the majority of tankers. The lines on the ship side are wrapped around winches. And when there's a certain amount of tension applied, those winches will render and start to release the line. So there's a factor for that as well. And I want to speak a little bit about what this equation means in the context of mooring analysis and the design of dolphins. So if we think about a ship at berth operating, so say it's an oil tanker and they're transferring cargo through marine loading arms, there are certain conditions, environmental conditions, that are acceptable for operations. There's limits to how much the ship can move up and down, side to side, before it becomes unsafe to operate to transfer cargo. And the same applies to limiting the amount of tension on each mooring line. So under certain design conditions, let's say the wind is blowing from right to left in that picture, pushing the vessel away from the berth, that may generate high line tensions. At a certain wind limit, at a certain limit, the tensions in the line become excessive. And the industry standard for mooring lines is to limit that tension for operational conditions to less than 55% of the minimum breaking load of the line. And that is what we've typically set as an operating limit for a terminal. Now, when we look at what the PIANC equation says is, if you look at the factors, the 1 and 0.6, what it's saying is that it's a situation where on a single mooring point, one line is tensioned all the way to 100% of its minimum breaking load. So it's at its maximum tension at which the line may actually start to part or break. And then all the other lines that are tied to that mooring point are tensioned to 60% MBL. So that represents an accidental and extreme, a very conservative scenario as far as how much load a Dolphin could see in its service life. Whereas the operational limits that we set for the operation of the berth, the loads are significantly less. And I want to spend a little bit of time to compare these two in practice. When we look at berths 4, 5, and 6, and the typical mooring arrangement, this is a berth 4 with a Panamax class tanker tied up. And you can see the mooring points are labeled MP1 through MP4. And MP1 and MP4 each have 4 head and stern lines secured to that one mooring point. And MP2 and MP3 both take the spring lines, which is 2 lines each. And when we look, I'm going to pull up the table of results here and walk you through it. When we run the mooring analysis, which again is, looking at wind, wave, and current conditions from different angles and calculate what the actual line tensions are in each of these red mooring lines, we can focus here on the first row, MP1 and MP4. You can see it's got 4 lines each. The minimum breaking load is 205 kips. That's about 93 metric tons for those who aren't familiar with kips as much. And when we look at the mooring analysis results, the maximum line tension for MP1 or MP4, we have one line at 54% of its minimum breaking load, and then lines lower at about 48, 26, and 20%. So one line is tensioned up to the operating limit, and then all the other lines tied to that same Dolphin are slightly less. They don't have as much tension. And when we sum those loads up, we get 303 kips applied to a single Dolphin as our load. And that's a load that I would consider a service load, an ASD load, something that this structure could actually see during its service life. And now I want to compare that to the load that we calculate using the PIANC equation. If we look at the number of lines, the minimum breaking load, and apply the PIANC calculation, we get a load of 573 kips, which is significantly higher. Now, if we take the service load that we get from mooring analysis and factor it up by this typical load factor of 1.6, we get a load of 485 kips, which is still significantly less than the PIANC load. So I just want to emphasize here that the load we calculate using mooring analysis is considered a service load that we can use in allowable stress design. It's a service load that the structure could see in its design life. And the PIANC load is an ultimate load that already has code resistance factors applied. It's a quote directly from the code after they list the equation. And for me, as a structural engineer, this is counterintuitive because we typically calculate a service load and then decide which is the appropriate load factor to apply in our design, depending on what type of structure, material, governing code that we need to comply with. But in this case, the PIANC load, we get an ultimate load already with code resistance factors applied, and then we need to interpret how to apply that in our design. And that's what I'm going to speak about next, is how we take these loads and apply them through in the design of a monopile and look at what the implications are of applying the service or ultimate load. So typical mooring analysis software that we use for single laterally loaded piles, L-pile, was used for this project, and its default is to use allowable stress design with service loads. And if we look, these diagrams on the right show the 303 kip service load that we got from a mooring analysis, and then the 573 kip load we get from the PIANC equation. And you can see the PIANC load gives roughly double the bending moment in the pipe pile. So if we carry that through to design, the table on the left here, we can get a 72-inch diameter, 2-inch wall thickness pipe pile to work in this case. That gives a total weight of about 125 short tons. And if we apply the PIANC load, it requires a significantly larger pile, 90-inch diameter, 2.5-inch wall, and the weight increases by about 70 tons of steel, which is significant. Now I want to emphasize here that the load that you apply needs to be compatible with your method of design. In this case, the PIANC load is an ultimate load, and we need to figure out a way to carry that into an allowable stress design in a compatible way. So that brings me to the next point. In this project, we looked at two different ways to approach this to achieve the goal of having a design load that's compatible with our method of analysis. And the first is to reduce that ultimate PIANC load to an equivalent service load or ASD load. So take the PIANC load that you calculate with the equation and reduce it down to a service load. Method two is to take the full PIANC load, apply it in design, but allow, or rather permit, an increase in allowable stress above the typical 60% yield stress that's specified in many building codes. So I'm going to speak first about method number one. We take the full PIANC load, which was 573 kips that I showed before, and reduce it by a factor of 1.60, which is a standard load factor for LRFD that's specified in the Unified Facilities Criteria, appears in Wharves, California Building Code, and several other U.S.-based codes. So that's the first method, is to reduce the ultimate load to an equivalent service load. And here we get 358 kips. Now I'll note here that reducing this load by a factor of 1.6, this is still greater than the 303 kip load we calculated for mooring analysis. Method two, we take the full PIANC load and apply it in design, but we permit a 1/3 increase in allowable stress. And this is in the provisions of the American Petroleum Institute practice for fixed offshore structures, where they allow a 1/3 stress increase. Now, I'll note that this used to be permitted by ASCE and the Steel Construction Manual. It's been phased out of these codes, but it's still permitted in certain circumstances. The paper I'll list below, it's got useful context for those who may be interested in how this stress increase has evolved over the years. But I want to emphasize here that these two methods can't be applied at the same time. If you take a reduction in the load using method one, you've got to stick to the allowable stresses that are specified in the code. And conversely, if you allow an increase in allowable stress, you can't reduce the load as well. So you can't double dip, essentially. So let's look at how these two compare for the 72-inch pile that we ended up going with on this project. If we look at method one, where we reduced that PIANC load to an equivalent ASD load, we get 358 kips and acceptable stresses. We have demand capacity ratio 95% relative to the allowable stress in the steel, which is 60% yield. We get a pile that's about 101 short tons. Now, for the same size pile, we hold the PIANC load at 573, but we permit an increase in allowable stress. Still results in excessive bending stress. We have a DCR of 120%. And a pile weight that's much larger because the tip elevation needs to drive down to get geotechnical stability. So even with the increase in allowable stress, still doesn't work. Method two would require a larger pile. So for this specific project, we recommended going with method one to reduce the PIANC load to an equivalent service load. It gives you a load that's compatible with your design. It's still very conservative compared to the service loads that we calculate in the numerical model. And it gives the deflections that we can rely on for design. Method two, we did not choose the ultimate load from PIANC. It doesn't really sync up with the ASD analysis, requires a much larger pile, and the deflections are not as reliable because it's an ultimate load. So I know we're pushing up on our hour time slot here, but I want to get to the fun stuff and talk about design here. In reality, rather than having continuous section of steel that's 2 inches thick, for this project, you really only need the thickest steel in the high moment areas, so we were able to taper down the wall thicknesses on top and bottom of the pile to reduce weight. The Dolphin top hat, which was one of my favorite engineering terms, is the concrete pile plug on top into which the anchor bolts for the bollard are cast. That's shown here. These piles were fabricated in Houston and shipped to site by barge. You can see here the bottom sections that are permanently embedded in soil are uncoated, and only the top sections from 10 feet below the mud line up are coated. Here you can see just what 2-inch thick steel wall looks like compared to my hand. Gives you a sense of levity compared to just flipping numbers in a model. And on the right, you can see the precision with which the coating is applied. Here, you can see they're cutting out the holes for the monopiles to fit in the existing wharf deck. You can see the contractor swinging the piles into place and readying the pile driving hammer. They drive one of the lower sections down to about deck elevation and then swing in the upper section and perform a field splice. You can see here a welder on the right splicing the two together. Then they put the hammer back on and continue the driving down to its final elevation. Here's a almost complete Dolphin on the left. It doesn't have a bollard on top yet. And then on the right, you can see the bollard is in place, but the walkways are not yet placed. This is before the contractor touched up the coating, so it looks a little scuffed up. And in the end, we went from having these 54-inch mooring cleats that were undersized for the vessels at this terminal, and in the end, we had a structurally isolated monopile Dolphin with a high-capacity bollard on top that's allowed the port to bring in these larger ships in a safer manner. So with that, that concludes my presentation. I want to thank again PIANC USA for inviting me to speak, and I'll happily take any questions now. Thank you.
Awesome. Thank you, Adrian. Yeah, we have a couple. All right. So let's start with the deflection question. So what is the ultimate or allowable deflection at the top of the monopile? And part two, what is typical for a monopile, or is it too broad of a question and situation dependent? So if you could talk about the deflections.
All right. So deflections are really dependent on where your monopile is. So if you're in open water and there's no adjacent structures, you're really just limited by, if you have walkways landing on the structure and what those connections can take when the monopile flexes. In this case, we're driving piles in the existing footprint of a wharf, and we need to make sure that when it flexed under load, that it didn't contact the adjacent structure. So in this case, we provided 2 feet of clearance on either side. So we limited the deflection in this case to 24 inches in any direction. And then what was the last question about a typical monopile? It really depends on, one, how many lines you need to tie around the mooring point. So if you have only 2 lines, the design load could be small. You could go with a smaller pile. And then it also depends greatly on how deep the mud line is. So what the cantilevered height of the pile is, and also how stiff the soil is. So it's hard to say. I've seen them, as small as, 48 inches, 54 inches in diameter, all the way up to a recent project we did in Louisiana with a 108-inch diameter monopile, so 9-foot diameter. So they can vary greatly.
Wow, good for you. There was a follow-up question. I think the photo at the end, there was like an optical illusion. It made that gap seem much smaller than 2 feet, but it was built with a 2-foot gap.
Yeah.
I can assume.
Yeah, someone noted that
right.
earlier. It's actually the gap is on the left is here and here, and then in the back side, because the monopile doesn't move back, it's essentially just butted up against the existing wharf. So. Got it.
Yeah, thanks. And then, so a question regarding method 1, can you speak to the use of unified facility criteria load factors versus ASC 7 load factors and reducing the ultimate calculated load per working group 153?
Yeah, that's a good question. I think that, yeah, that's a very good question. So in UFC, the load combinations specifically have, a line item for mooring loads applied to a Dolphin, and they have got the factors for ASD of 1.0 and a load factor of 1.6 for LRFD. So you can approach it from that angle, looking at, the actual mooring loads, whereas an ASCE 7, because it's not specifically written for structures of this type, the argument is more from a perspective of what drives the mooring loads. So, for example, the wind load, current load, or wave loads that actually move the vessel, the ship itself, and drive those mooring line tensions. So I think the argument can be made from both sides. I think the argument is a little easier and more clear to make from the UFC perspective, but I think an equally valid argument could be made by taking a reduction based on wind loads applied to the vessel that generate line tensions. So both are valid. Just depends on which argument you want to make with whoever is reviewing the calculations.
Got it. Thank you. So let's do one more question. We're running a little bit late on time, and then we'll have one more chance to ping any questions at you after our closing slides. The question is, did you have any issues rolling 2-inch thick plate in the pipe pile? Part 2, what method was used to roll it, and was there a specific reason for the site welding of the splices?
All very good questions. The first one for 2-inch thick plate, that was no problem for the pipe pile manufacturer in Houston. I think they can roll up to 3-inch thick plate. The pipe is, I guess the steel is manufactured in flat plates. You can see here these 10-foot sections, they call them cans. So it's flat plate, 2 inches thick. They roll them in the shop and do a longitudinal seam. So they roll them up essentially into 10-foot cans. It looks like a Coke can. And then they splice them together in the shop. And then the section, so the reason that we had field splices is because you can see here, it's in pretty small text, but each of these two sections, there's 2 sections spliced together in the field. One of them weighs about 42 tons and the other one's 56 tons, and the piles were quite long. So it was difficult to transport at one piece, and also difficult for the contractor to swing them up into place, get the leads of their crane high enough to pull the pile up in one piece. So it was easier for the contractor to drive, to break it into 2 pieces.
Got it. So thank you, Adrian. Let's transition to our closing slides, and then we'll have one last chance to ask Ben and Adrian any last remaining questions or open discussions. So Nick is going to tell you about our upcoming events.
Hello, my name is Nick. We are planning a similar webinar in the spring of 2021. It will be set up very similar to this, be a little more technical. Right now, we are tentatively planning on having Matthew Schipper from TU Delft talk about a project that's called Sand Motor. It's a mega nourishment beach project in the Netherlands, and it's a way to passively work with nature to encourage beach nourishment and reduce coastal flooding. And with that, I will pass it to Nicole, who's going to talk about if you're interested in getting involved.
Yeah, thanks, Nick. So one of the best ways to get involved with PIANC is to join a working group. It's a great opportunity to collaborate with talented individuals on a topic that interests you. And there is a young professional seat in every working group. The working group vacancies are listed on PIANC USA's website under the News and Events page. And we're actually going to extend the current working group vacancies through next Thursday, December 17th, if anyone's interested in applying. Another way is to apply for a leadership position in PIANC. Andrea, who's been our West Coast representative for the last 4 years, is about to end her 4-year term. So there'll be an opening next year in PIANC USA YPCom. And then to close with the theme of today's presentation, you should write a paper for the 2020 Paepe-Willems Award. To do that, you submit a 3-page abstract by next August 31st, and final papers are due 1 month later on September 30th. Additional information on how to apply is available on PIANC's website under Awards. So that concludes our presentation, and I'll go ahead and pass it over to Kayla to close it out.
Great. I just wanted to say thank you again to our presenters. Thank you so much, Ben. Thank you so much, Adrian, for taking time out of your day today to share with us about your work. We're so appreciative. On the screen in front of you, you can see the contact information for our two presenters from today. You can also see the contact information for our leadership team. So if you do have any questions about PIANC, about joining as a young professional, you can definitely send us an email and we will get back to you. Our social media information is also on the bottom here, so you can see, you can connect with us via social media, or you can visit us on our website, which is also posted there at pianc.us. And also just a reminder that this webinar is being recorded and we will be posting it on our YouTube page. So if we do some questions here in a little bit and you can't stick around, you could always tune in via YouTube to watch the remainder of those questions. So again, thank you so much for your time. Our presenters have agreed to stick around for a few more minutes. So we encourage you, if you do have some questions that you've thought of, go ahead and send those in the chat. And anything we can't get to, we will try and answer via email. So thank you for your time. Go ahead and send your chat questions in.
Matt, I think you're muted.
Oh, thank you. Great presentations. Ben, I had a question for you. We have all this great information, great data now. What are we doing with it? What are the next steps?
So we've actually, and since that work's kind of concluded, we've been in touch with a couple of the ports here in New Zealand that have actually asked to do specific site modeling of a similar variety, just to assess the existing infrastructure there. The other thing is, I would say for the organization I work with right now, I'm kind of a bit of a jack of all trades, to be quite honest. Right now, I do a lot of different things, but we do a lot of different types of vulnerability assessments and development of damage models and this kind of thing for a lot of different types of infrastructure. And one of the key consumers of that kind of information is actually insurance companies when assessing insurance policies and premiums and stuff like that for the port companies. So there are organizations, at least in a New Zealand context right now, that are kind of taking that on in the early stages. But there are opportunities on the horizon for that to be applied in a number of different ways.
Got it. Thank you. And then we have a question for Adrian. Christine Smith beat me to it. If you can talk about fatigue and cyclic loading with the piles and the pile splices, and what kind of weld did you specify?
Hey, can you all hear me? I was uncovering myself from the multiple levels of mutes.
We can hear you. We can't see you, though. It's more important that we can hear you.
Yeah. Okay. So the first question was fatigue, and the second question is weld. So in this case, this maximum load that we're looking at, the PIANC load, is typically, I guess I would consider it an extreme load that would not happen many times during the design life of the structure, and certainly not in a cyclical nature. However, the smaller loads from mooring, so for example, the lower service loads that we'd get from a typical operation, we did look at lower magnitude loads in a cyclic fashion in Alpile, where you can actually look at the soil response from cyclic loading. We didn't have any concerns with fatigue in the steel or in the welds, but we did look at cyclic loads of a lower magnitude, but not for the ultimate PIANC load. And then the field splice used full penetration butt welds around the full circumference in the field.
Got it. Thank you. And then following up, Adrian, so that project was down in Louisiana. I'm up in New York, and I just don't think we can get 2-inch thick steel pipe piles and a cost and have it be cost effective. Maybe we can, but I know I hear a lot of complaints from contractors. I guess just like to hear your thoughts on, maybe transportability of that design around the country versus, numerous smaller piles from a cost perspective or engineering. Just your thoughts.
Yeah, it's a good question. I think moving to very large diameter piles in certain locations, could reduce the number of contractors that could really bid on the work or drive up the price of the piles for the project. And I guess historically, in the Gulf Coast, the contractors and pipe pile manufacturers down there are very used to this size pile. And we're starting to see more and more contractors on the West Coast, capable of procuring this thick steel and driving these piles. But I know in different locations, in the Northeast, it's not as typical. I'm not as familiar with the different steel manufacturers in the Northeast, but, for these types of projects, if you could only procure them in a southern location, it might be difficult or prohibitively expensive to try to ship them across multiple states, and you might be better off going with multiple smaller diameter piles. So it certainly is a consideration, but at least on the Gulf Coast and West Coast, there's a lot of contractors who are very capable of procuring and driving these size piles.
Mm-hmm. Got it. Thanks. Did you mention what kind of hammer they used?
They used a diesel impact hammer.
No vibratory hammer at all?
Nope. Yeah, it was a very large diesel impact hammer. I can pull up a photo if you'd like. If
your screen share is working.
Yeah, I've got it right here. If you got other questions in the meantime, I can ask him when we pull one up.
Cole, Nick, Brian, you've given us some good ones. Oh, yeah.
I think I've got a photo of the hammer on the barge. Gives you a better view, but I'm struggling to find it.
Mm-hmm.
Yeah, very large impact hammer.
Yeah.
Very loud. Yeah. But the pile's awesome. Actually, it's pretty soft clay at this location, and the pile actually settles quite a lot under its own weight until you have to start driving it.
How many of those did you end up installing for this project?
8.
Oh, what did you mention the contract value or construction value?
It was about $2.5 million total. So just the monopiles, bollards, demolition, and then some cleat repair and walkways. Yeah, about $2.5 million.
So $250,000 per monopile-ish? Right?
In that range. I need to look back at the bid tabs for the project, and we could catch up on that offline. But that's kind of the rough order of magnitude for the project.
Yeah, that's good to know. Okay. Well, I don't want to keep everyone longer. I don't see any new questions coming in, so I think we can thank our presenters one last time and come to a close. So thank you again, Ben. Thank you again, Adrian. It was terrific.
Yeah, thanks for having us. That was fun.
Yeah, thank you so much. It's been great.
All right. Well, we'll bring it to a close. Right. Thank you, and hope to see you at the spring webinar.
All right. Take care, everybody.
See you, everyone.
Goodbye, everyone.
Bye. See you later.
Bye.